Hey everyone, welcome back. Continuing with our practice test for chapter 11. We have this problem where we are to find d squared y dx squared in terms of t if x is t squared over 2 plus 4t and y is t squared over 2 minus 9t. Like every other problem with the second derivative, the first thing we're going to need to do is find our first derivative dy dx. Now for parametric curves, that means we're going to need to find dy dt on dx dt. That just means, of course, that we're taking the derivative with respect to t of the equation for y over the equation, the ddt, the derivative with respect to t, of the equation for x. We'll substitute our equation for y, and then we'll substitute our equation for x. And then we'll take our derivatives. Fixing a little bit of a typo there. And then we can just simplify from here. And that gives us our dy dx. dy dx is t minus 9 over t plus 4. Now that is our start. Let's put that over to the side, and let's try to figure out our second derivative then. The second derivative, d squared y over dx squared, well, that's equal to the derivative of dy dx with respect to t divided by dx dt. Now this equation is not at all intuitive to most people. So this is one that you're going to have to be very deliberate about whenever you're taking a second derivative. Let's start substituting things in. First of all, we have our equation for dy dx. And then from here, we also know what dx dt is. We figured that out when we found the dy dx equation. Dx dt, if we just keep following the denominators across, that's just t plus 4. Now the only thing left to do is to find the derivative of t minus 9 over t plus 4 with respect to t. We're going to have to use the quotient rule here. So the denominator, t plus 4, multiplied by the derivative of the numerator, which is 1, minus the numerator, t minus 9, multiplied by the derivative of the denominator, t plus, the derivative of t plus 4 is just 1, multiplied or divided by the square of the denominator. To simplify this, we're going to, instead of divided by t plus 4, we're going to multiply the numerator times the reciprocal of the denominator. And we can collapse that down, and that gives us a t plus 4 cubed on our denominator. Let's clean up our numerator. Multiplying everything by 1 doesn't really matter. And that gets us to a second derivative of 13 over t plus 4 quantity cubed. All right, let's take a look now at number 12. The velocity vector of a particle moving in the plane is v equals e to the t minus 4t, e to the t plus 2t, with an initial position of 6, 5. Find the position at time t1 equals 5. So initial position, 6, 5, that just means that x0 equals 6 and y of 0 equals 5. Now we're going to take each of these components separately. So let's start with the x coordinate. We'll use the fundamental theorem of calculus with x prime. We know x of 0 equals 6, so we'll make our value of a 0. And we're interested in the position at t equals 5, So we'll make our other time b equals 5. Next, we have an equation for x prime. It's given to us in the velocity vector, and it's just e to the t minus 4t. Now we just have to integrate e to the t minus 4t. Now we know x of 0 is 6, so we'll substitute 6. And then we'll evaluate that definite integral. Now we're going to do a little bit of evaluation. And then a little bit of solving. This gives us our first coordinate, the x coordinate. The x coordinate at t equals 5 is e to the 5th power minus 45. And then we do the exact same thing for the y coordinate. Compute our antiderivative. Substitute. And then evaluate. And then finally solve. So the position at t equals 5 is x of 5 comma y of 5. I guess technically not a vector. And that's equal to e to the 5 minus 45 and e to the 5 plus 29. So there's our position vector. And we are rolling now. Let's get to 13. Find the derivative in terms of t for x of t. X equals natural log of 5t, and y equals natural log of the 9th power of 7t. Now, I've talked about this a few times, but whenever I see these natural log functions, and I know I'm going to have to take a derivative, it's a good idea to simplify them first. So for example, the natural log of 5t, that's equivalent to the natural log of 5 plus the natural log of t. So if I want to take the derivative of the natural log of 5t, I could equivalently take the derivative of natural log 5 plus natural log of t. And what's nice about this equation is the derivative of natural log 5, well, natural log 5 is just constant. So it's just the same as the derivative of natural log t, which is 1 over t. Let's do the same thing with the y coordinate now. So the natural log of the 9th power of 7t, that's equivalent to 9 times the natural log of 7t, which is equal to 9 natural log of 7 plus 9 natural log of t. So the derivative of the natural log of 7t to the 9th, that's equal to the derivative of 9 natural log 7 plus 9 natural log t. And we know 9 natural log of t is constant, so that derivative is 0. And the derivative of 9 natural log t is 9 times the derivative of natural log t, which is just the same thing as 9 multiplied by 1 over t, or just 9 over t. Now that we got the individual derivatives out of the way, let's get to the slope formula. The slope is dy dt over dx dt, which is the derivative of the natural log of the 9th power of 7t over the derivative of natural log of 5t, which is 9 over t over 1 over t, or just 9. All right, one more to go in this video. We've got the rectangular equation for the polar equation r equals 5 cotangent cosecant theta. So to do this one, let's start off by looking at our normal conversion from polar to rectangular. So x is r cosine theta and y is r sine theta. We're going to substitute now for r. We know that r is 5 cotangent cosecant. Now, it might be easier to see what's going to happen if I take all the cotangents and cosecants and write them in terms of sines and cosines. First with the cotangents, and then with the cosecants. And then we're going to multiply everything together. So sorry about that. Somewhere along the way, all of my thetas turned into x's. Okay, so this, I don't know if this seems promising to you, but I can see how this is kind of promising. Let me, first of all, let's rewrite these in terms of cotangents. So we can see, first of all, that x is cotangent squared theta. Sorry, 5 cotangent squared theta. And we can see that y is 5 cotangent theta. So I'm going to solve for cotangent right now. In my first equation, I get x over 5 is cotangent squared. And then in my second equation, I have y over 5 is cotangent. Now, if I decided to, and I'm going to decide to, if I square that second equation in terms of y, look what happens. I get y over 5 squared equals the square of cotangent theta, which I can further simplify as y squared over 25 is equal to cotangent squared theta. Now you might be saying, so what? Well, x over 5 is equal to cotangent squared theta, and y squared over 25 is equal to cotangent squared theta. So y squared over 25 is equal to x over 5, or just y squared equals 5x. And that is pretty much where we want to stay with this one. If we wanted to square root it, or if you decided to square root, you would be losing part of this curve. So this isn't really a function, but it is an equation in rectangular coordinates. I think this would turn into a horizontal parabola. Yeah, of course. So that takes care of question 14. Next time we see you, we're going to be doing questions 15 and 16. So have a good one.